All right, so concavity and points of inflection here. Would everyone agree that this is concave down?
Yes.
Okay, now try to connect this to something you already kind of understand. This is concave down. It looks like a frown, right? Concave up looks like a cup. That's how I remember it. Okay. So that's concave down. This is also kind of like what your rocket looks like, correct? Okay. If we had to sketch the derivative of this, this is just a parabola. What did your derivative look like for this? It's linear, right? There is 0. And it's linear going down. Because here it's decreasing, here it's increasing. Right? So this was f prime of x. All right. If we had to derive this, if we had to derive f prime of x here, it would be a horizontal line, and what would it be? The acceleration, right? In this case, it's going to be negative 32. Okay. Our original equation was the height of t was negative 16 t squared plus whatever your starting velocity was, 70 t plus whatever the starting height was, we'll say it was 1.5 feet. We derived it. We got negative 32t plus whatever your starting velocity was. Now that tells us our velocity at any given moment. Okay? We derive it again, and you're going to get acceleration. Derive that, and we're just going to get negative 32, right? So what this is telling us is, if it's concave down, the second derivative is negative. Okay? F of x is concave down, then f double prime of x is less than 0. Now, we can think of f double prime of x as the slope of f prime of x. It's just the derivative of f prime of x. Okay? You notice here how f prime of x was decreasing, right? So we can think of it as when f double prime of x is less than 0, or when f prime of x is decreasing. Our velocity here was decreasing, right? Our velocity was decreasing because gravity was pulling that rocket down to Earth, right? If you're taking physics, you know that gravity pulls at negative 9.8 meters per square second in metric, or negative 32 feet per square second in imperial units. Okay? So when your velocity is decreasing, it's concave down. Or we can basically find it when f double prime of x is less than 0. Okay? Extending that a little bit, if f of x is increasing, is concave up, then f double prime of x is greater than 0, and f prime of x is increasing. actually this shouldn't be just if, it should be if and only if. If and only if. This is the big idea we have going on here. And when it switches from concave up to concave down, or concave down to concave up, this point right in between is called a point of inflection. So when f double prime of x is equal to 0 or undefined. So basically what we're going to do here is the same thing we just did with increasing and decreasing, okay? Except we're going to be using the second derivative. We're going to use the second derivative. Not too bad. The tricky part will come in is when I just give you a graph and I set the graph of f prime and say, when is f concave up or concave down? That's when you're going to start confusing all of them. They're all going to run together, okay? That's going to be the frustrating part. We're going to make a big, huge table to kind of fit everything, help you fit everything together, okay? And it's going to be precious. But the table will help greatly. All right, we're going to start off with just doing it analytically, though. Find all points of inflection and for f, and when f is concave up and concave down. And we'll say f of x is equal to, we'll just do a nice simple one here, x to the fourth minus 4x cubed. All right, so first thing we're going to do, we're going to derive it. F prime of x is equal to, shout it out, anybody, 1, 2, 3. Okay, these are nice easy ones. I'm not making you do product rule or quotient rule or anything. Now that tells us when that would tell us when it's increasing or decreasing, right? If we graph this, we could actually look at it and find out when it's concave up or concave down. But we're going to go ahead and take the next step here. F double prime of x is what? All right, got to find when this is 0 or undefined. Well, that's never going to be undefined, is it? So we're going to get 12x squared minus 24x. So we're going to get 12x times x minus 2. Still with me? So what's going to happen at 0 and 2, right? Okay, so once again, you can just pick points in between, right? You just pick points in between. What's happening at -1? Now, let's see here. This is even easier to plug it into, isn't it? That's going to be a negative. That's going to be a negative. So it's going to be two negatives make it positive. At positive 1, it's going to be positive and a negative, so it's going to be negative. Oh, and using the big numbers, it's going to be positive, right? Once again, we can use Julie's method and say, well, once you've got it factored, it's positive and positive, right? So it starts positive. Are there any double zeros in here? Nope. So go positive, negative, positive. Okay. So that means F is going to be concave up. It's concave up along here. It's concave down along here. Concave up along here. In physics terms, it's accelerations in the positive direction, accelerations in the negative direction, and accelerations in the positive direction again. Okay? Think of it like being on yo-yo. So maybe you stretch the spring out, it's accelerating up. Then it would start accelerating down as a free fall, right? And it would stretch, and then it would start accelerating up again. So when it starts getting right around here, it starts slowing down. That's when the acceleration is actually going up. Yes?
So since it's the second derivative, those are not the maximum and minimums, though?
No, those are not maximums and minimums. However, though, you lead us to a great point, though. If we know something's concave down or concave up, you can actually figure, if you know the zeros if you know the critical points, you can find out if it's concave up or concave down. I'm sorry, you can find out if it's a maximum or minimum based on the concavity. We're going to talk about it tomorrow. Good point. Okay? So this is the basic idea here. Extending this to graphs, though. Once again, you're going to keep this idea in mind right here. Okay? F is concave down when f double prime of x is less than 0, or when f prime of x is decreasing. Here's the graph of f prime. This is the graph of f prime of x. When is f concave down? When is f concave up? And what are any points of inflection? Keep these two big ideas in mind right here, okay? I want you to talk with your team using this, especially this, okay? When is the original graph of f concave up or concave down? Take about 30 seconds, talk with your team. All right. F of x is concave down when f del prime of x is less than 0, or when f prime of x is decreasing. When is f prime of x decreasing? From here all the way to 4. So it's concave, f is going to be concave down when f prime of x is decreasing. So from negative infinity to 4, it was increasing from 4 to 5, 6, 7, 8, 9. F prime of x is increasing. It was decreasing for here to here, 9 to 11. Then it's increasing again from 11 to infinity. So when f prime changes, though, from increasing to decreasing, in between we said there's a point of inflection, right?
Pardon the interruption, but I have the following
1,
announcement
2,
to make.
3.
Again, a reminder that tonight at 7 p.m. is the bully prevention concert in Parker Auditorium.
You'll notice points of inflection occurred at, what are these on F prime here? They're relative maximums and minimums, aren't they? Because at relative maximum minimums, F, the derivative is 0 or undefined. It's just weird because we're taking the derivative of a derivative here. All right? We'll pick this up again tomorrow.